Late. I think we're going to reverse things today. I'm going to teach you the new lesson, and we're going to do the questions at the end. Otherwise, I never quite know if I can get everything done. So let's see how that works. I hope it doesn't work too bad for you. Yeah. I haven't decided yet, honestly. I will get to it though. But anyway, let me get to the new stuff and then we'll go backwards. Okay, the new stuff today. Oh, and a general comment. We're going to spend 2 days on lesson 3.4. So I guess I was a little bit weird when I said finish. We'll get most of it in today, but we need to live with this assignment for 2 classes. And then we're going to do 4.1. And then Monday, I really need to start trig. So just so you know, I'm keeping an eye on the overall schedule. That's reserving enough time for semester review and those types of things. Michelle? Okay, let's do that. Let's see, is that carving? Not a real simple thing, but we'll just do this. Yeah. Okay. Fundamental theory. So as you can see, there's 5 things listed here. I'm not going to do the bottom one. These are all tools that help you learn how to graph and understand functions. And the bottom one is, it's just not that important, so I probably won't get to that. But the other 4 we should get to. So here we go. The first one is called the Fundamental Theorem of Algebra. It's in your book on page 293. And it says a lot of things, but you know, the really bottom line is, whatever degree the polynomial is, that's how many complex solutions there are. So in other words, if there's a second degree polynomial, there are guaranteed to be 2 complex solutions. If it's a 7th degree polynomial, there are guaranteed to be 7 complex. Now notice I'm saying complex. So that means if you count all the imaginary answers, there's that many. Also, if there's an answer that has a multiplicity in it, I'm counting all the multiplicities. So for example, let's say you had a cubic function that was factored as x minus 1 times x minus 1 times x plus 1. Well, then the x minus 1 shows you what? That there are 2 answers of x equals 1, a multiplicity of 2. Well, that's 2 answers. And then that third one, what did I say? X plus 1. So that solution is minus 1. So with multiplicities, we count everything in the multiplicity. Okay, so this is pretty important. It says that when we try solving some of these polynomials of higher degree, the number of solutions there are is what the degree is. Okay? And if we have, so now we know how many solutions to look for. Now it doesn't say how many real ones there are, but it says how many complex ones there are. Okay. We're going to make use of that as we start working on some problems today. Here's just, I guess we're on to test 2 now. The second item on the thing is called the rational zero test. As we start looking for answers to these larger degree polynomials, how in the world do we know what is a viable candidate? If we're going to just sit there and try all these factors, we could grow very old very quickly. And so, how do we know what to try? Answer, make use of the rational zero test. I'll just give you a quick look at what it works like. When you have your polynomial written out, as I have a sample here written out, there is a coefficient of the highest degree term. We nickname that Q. And there's a constant term way on the end. If there isn't, it's a 0. You know, with an exponent of 0, 5x to the 0, we call that guy p. And for all the different possible combinations of p over q, we look at the factors. You know, what are all the factors of p? What are all the things that divide evenly into 5? Answer, really, plus and minus 1. You know, 1 always works. And plus or minus 5. Okay? For q, what are all the possible factors of 3? Again, plus or minus 1, plus or minus 3. Now, what are all the possible fractions of these guys over these guys, of the p guys over the q guys? Well, we could have plus or minus 1 over 1. Of course, what's 1 over 1? 1, right? And then you got plus or minus 1 over 3, plus or minus 5 over 1, and plus or minus 5 over 3. So it's like all the possible p factors over all the possible q factors. Now, so what this means is, in this particular polynomial, if I was trying to find factors of it, the only numbers I should really consider are these. It's silly to waste time, for example, on 6. 6 is not in our list. And so, as we, let's see, let me also tie this in with the previous thing. Do you remember how we can tell if a number is a solution? We learned something really cool in the last class. What was that? I don't care if you remember what it was called, but, you know, like, how could we tell if 2 is a solution of a polynomial? Answer? Just plug it in. Find f of 2. And if the answer comes out to 0, that means the remainder is 0, and that works. So, that's cool. So all I got to do is try a bunch of factors, but still there's an infinite number of factors to try. So instead of trying them all, try these guys. Try the ones from the rational 0 test. And what we're telling you is, you want to waste less time? These are the guys to try. They still might not all work, but these are the candidates that have a shot at it. Okay, and and try the easy ones first. So, for example, one of the first things I would try is plus 1. And then if that doesn't work, I'd try minus 1. Because those are nice, easy numbers to calculate with, right? It's easy to find f of 1 and f of minus 1. If I have to, I'll go to the fractions, but I think I'd try the next whole number, 5 and negative 5. By then, you may not even need these other two, as you'll see as we go on. But at least we've cut this list down from an infinite number of things to try to what? 8? We got it down from infinity to 8. That's pretty darn good consolidation. Okay, so that's a tool we're going to make use of today. And by the way, in a little while, we're going to just dive into some problems, and I'm going to show you how you can make use of this. And maybe now is the time. Okay, so let's dive into this one, even though I don't have them all out yet. Here we have a polynomial. I guess it's number 66 in the 3.4 assignment. Okay, so how in the world can I factor this thing? Well, I could try what? Putting it in groups and divide and conquer, but I don't think that's going to lead me anywhere. So let's make use of this rational roots theorem. I'll just remind you how it works. Let me get a writing utensil here. Okay, so this guy over here, you can always think of when there's no number out there, of course we can think of it as a 1. So that's like my Q guy, and my P guy is sitting over here. He's the guy that has x to no power, to the 0 power. So I got my P and Q guys. So let's write those down over here. We got P is 35, Q is 1. Now, what are all the factors of 35? Well, let's see. We always got 1. We know that. What's the next whole number that divides evenly into 35? 5, right? And then wouldn't that leave what? Plus or minus 7. And then, I don't think I've missed any, have I? 7, 5. Is there anything else that divide? Yeah, I think that's it. Okay, now this is easy. What are all the factors of 1? Okay, so no big deal. Now let's find the P over Q kind of possibilities. So now, thinking of all the possible P's divided by all the possible Q's. Well, the good news is there only are 2 Q's, so this is going to work out pretty nice. So we've got the possibility of dividing this P by this, so you got plus or minus 1 over 1. Isn't that just plus or minus 1? Then you got plus or minus 5 over 1. So because this is plus or minus 1, I really have it easy here. I don't even have to consider this, do I? Because isn't that just going to change the signs? So these are the candidates that I should use for solutions. 1, 5, 7, and 35, plus or negative. All right, now, let's try those. Let's start with the small one, 1, and let's see if 1 is a solution. Do you remember the old technique for doing that? Let's plug in 1 for every x, and let's see what we get. And that'll be our remainder. So let's try doing that one in our heads. 1's pretty easy. 1 cubed is what? 1, and then here we're going to have 9, and 1 plus 9 is 10, and 10 plus 27 is 37, and 37 plus 35, it's sure not 0, right? So what does that mean? 1 is not a solution. All right, let's try negative 1. What happens when we plug in negative 1? I'm going to write these out. Negative 1 cubed is, and then this will be plus 9, because when you take a negative 1 squared, it'll be a positive 1, right? Okay, then this will be minus 27, and this will be plus 35. And what do those add up to? Well, we still don't have a 0. We're getting closer, though. Now we've got what? Plus 44 and a minus 28. So that won't work either. All right, on we go to 5. Now, I'm not even going to try the positives, because if I plug in a positive 5, aren't these just all going to be very high positive numbers? Does that make any sense to you? So I'm not going to try 5. Let's try negative 5 and see what happens. All right, now these are going to get a little big. What's negative 5 cubed? Well, 5 squared is 25, and 25 times 5 is 125. So that would be a negative 125. Okay. Now, 5 squared is 25, and what's 25 times 9? 225. Now, what's negative 5 times 27? Negative? Thank you. And plus 35. Okay, we have negative what? Negative 160. Still no go, right? 260, thank you. And what do we get on the positive side? So what does that mean? That means that negative 5 works. Okay, this is really cool. We have just found one of the solutions. So we use 2 tools to do this. This at least narrowed the candidates down to less than an infinite number. And then we used our good old remainder theorem to find out if it works. All right, now, besides being happy because we just found a factor, let's write it down. We know that's one of the factors. I'm going to just write it down. Now, what I'd like to know is x minus 5 times what? Well, can't I just do synthetic division to find out the other guy? So let's do that down here. Yes. Thank you. It's x plus 5, because then the solution would be negative 5. Thanks, Emily. What's the polynomial? We got a 1, a 9, a 27, and a 35. And what are we trying? Negative 5. Should work. Let's just see what happens. Bring down, multiply, add, multiply, multiply. Yep, there it is. 0. Remainder, just like we said. So now I know the rest of it. It's 1x squared plus 4x plus 7. We just factored that beast. And that's what's basically what we have to do with these things. All right. Now, what am I going to do with this? Can I factor that further? Well, what can I always do with a quadratic? I can find those two solutions using the quadratic formula, can't I? So let's finish this off. So let me just let's write this down. We know that this solution is -5. Now we're going to use the quadratic to get this down to the final two solutions. So here we go. X equals minus b plus or minus square root b squared minus 4 times a times c, all over 2 times a. What happens in there? We have 16 minus 28, which is a -12. So we have -4 plus or minus the square root of -12 over 2. Of course, that's going to be imaginary, but that's okay. Remember, what did the fundamental theorem of algebra tell us? It said we are guaranteed with a third-degree polynomial to have 3 complex solutions. Complex. So they may not be real. We got one of them. The other 2 are right here if we just go a little bit further. So let's simplify that. Well, what can we do with -12? We could think of that as what? 4 times, how about let's say -1 times 4 times 3. Okay? And what's the square root of -1? And what's the square root of 4? And what's left? And then we could just simplify by factoring a 2 out of the top. Okay. Now we got our 3 solutions. Here's one, and here are the other 2. Total 3. So we just made use of the rational roots theorem and the fundamental theorem of algebra to come up with those. Of course, let me just make a little comment about these. This is a crossing point on the x-axis. Imaginary numbers are not crossing points on the x-axis, even though they're complex solutions. The graph that you and I have grown up with is a real number graph, and so these guys are not what? Crossing points. So they don't help. These don't help us with the graph. This one does, but we do have all the solutions. All right, let's. Did everybody get that and move on to another one? Okay. Now, as you can tell, this can go up in complexity. All right. So what I did is I just put a rather obnoxious polynomial up there. Okay. And you were asked to solve it. Now, you don't write this one down. Let's just use it as an object lesson. Okay? First of all, you notice it's a 7th degree polynomial. Therefore, the fundamental theorem of algebra tells us there are exactly 7 complex solutions. Okay. Wow. If I had to factor this beast, I would first want to use the rational roots theorem and identify -5 as q and -24 as p. And then I'd want to break 24 and 5 down into their factors. Okay, and you see I've done that. Unfortunately, 24 has lots of factors. Fortunately, 5 has very few. But when you put those all together, do you see that these are all possibilities here? I mean, you got to take all of these, this over this, 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 and you just got to keep going. And you got to simplify them. All right, so we got whatever this is. Those are all candidates. All right. So anyway, I just wanted to show you another example Here's where you're really happy when you have numbers that don't factor real well, because then it really cuts down the number. Okay. Then, another interesting creature is the conjugate pairs theorem. And I put this in my own simplified terms in the box. If you've got one imaginary solution, then I guarantee you've got another one. It's the conjugate. They always have a conjugate pair, every single time. If you have an imaginary solution, they're guaranteed to be another one. So in other words, they always come in pairs. Imaginary answers always come in pairs, and that's why it's called the conjugate pairs theorem. So if by some reason we found one imaginary answer, automatically you know that there's another one. And we're going to make use of that. That's kind of handy to know. So you cannot have an odd number of imaginary solutions. There has to always be a pair. All right. And then finally, because I'm not going to do bounds, there is something called Descartes' rule of signs. This one's going to take a little while for me to explain to you, but here's how it works. This is a clue as to how many positive and how many negative solutions you have. And what kind. You know, for example, well, what was I going to say? We got positive, negative, and yeah. So we know there could be imaginary. We have three categories: positive, negative, and it could be imaginary. All right. Here's how this works. You write your polynomial down, and you literally count how many changes in sign there are from term to term. For example, let's look at this one. From here to here, we have one sign change because we went from a negative to a positive. Okay, so 1, another sign change, 2, another sign change, 3, another one, 4, another one, 5, not, and we have another one on the end, right? 6, did I count right? Okay, now, I know you're not going to love this, but here's how this works. Whatever number we came up with, 6, there are that number of positive solutions or any even number 2 less than that. So in other words, there could be 6, there could be 4, there could be 2, there could be 0. It doesn't make sense to talk about a negative number of something. So let me just go through that again. Take the original function and count the sign changes. Okay, we got 6. That tells us that for positive solutions, there are either 6, 4, 2, or 0 of them. Now, there's a second part to this, and then we'll actually do one, okay? So just try to make any sense out of this right now. I know it sounds complicated. Yes?
What if it's an odd number? And you take 2 less.
Yeah, if you got 5, then it's 5 or 3 or 1. You just always keep going down by 2s. Yeah, if it's an odd number, he was just saying, just keep going down by 2s like that until you can't do negatives. All right, now, that's how you find out how many positive solutions, but how do you find out how many negative solutions there are? Answer, you've been given f of x. First, find f of negative x. So that means everywhere there's an x, I've got to plug in a negative x. Do you see why this changed? Because what happens when I take negative x to the 7th power? That's going to be a negative, right? And a negative times a negative is a? Do you see why that changed positive? Why does this one not change? Because what's a negative number taken to a 6th power? Still, it's positive, right? Yes? Because it's to an even power. And what happens here? When you take a negative number 5 times, you're going to get a negative, and a negative times a negative is a positive. So you see how this changed? Okay, so just go all the way through and write f of negative x. Now count the sign changes again. None, 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 1, 1. So we got a total of 1 this time. That means we have one negative solution in this problem. By the way, I don't have to go 2 below that, because if I go 2 below 1, I'm under 0. No.
In the equation at the top, or polynomial, why did you change it from square from a squared to 7 because they're both positive signs? Why did you still count that?
Say that again, please.
Going from the negative x, not negative, the positive x squared to the positive 7x. Why did you count that as a sign change?
I don't believe I did. Okay, here we go. 1, 2, 3, 4, 5. 5, I didn't count it. 6, but this one I did have to count. So the answer is I didn't. But that would have been wrong, yeah. Okay? Now, let me show you how to put this together. I know this is kind of overwhelming at the moment, but let's just dive in and do an example, okay? Let's start off by doing Descartes' rule of signs. All right? So what I'm going to do, and this is the way I recommend you do Descartes' rule of signs. You make a little chart and say positive, negative, and then we're going to leave a column for imaginary. Those are the only 3 possible kinds of solutions we're going to classify. Positive, negative, or imaginary. Now, let's go up and do our sign change count on the current one. Okay, we have none, 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 none. So, how many positive solutions are to this? Okay, that was easy. Okay, now let's find f of negative x. Okay, what happens when you take negative x to the 4th power? It's going to be a positive, right? Okay, then what happens when you take a negative x to the 3rd power? That's going to be a negative x cubed. So isn't this going to be minus 6x cubed? Okay, and in the 3rd term, when you take a negative and square it, you're going to get a positive. So this is going to be a negative 6x, and that's going to be a plus 9. All right, how many signs? Is everybody with me on that? No? What did I? Everywhere there was an x, I was plugging in in parentheses a negative x.
So the top one, is that same case as the 1 next to the 4?
That's a very crippled equal sign is all that is in front of the 1.
So it's
My apologies. That's just a 1. So all I was doing is saying, what's negative x 4 times? Oh, that's going to be a positive x to the 4th again. What's negative x cubed? Well, that's going to be a negative. And what's a negative times 6x cubed? It's a negative 6. So okay. Now how many sign changes do I have here? 1, 2, 3, 4. That means for negative solutions, I either have 4, or 2, or 0. Now, we already nailed this down. We know that the positives are 0, so I'm just going to reinforce that. We're trying to show, see, what each line in this table represents is a possible scenario. Okay? Now, think this through. What degree is that polynomial? 4. So how many total solutions must there be if we count all the complex ones? 4. Okay? So in the top line, what do I already have a total of? 4, right? 0 plus 4 is 4. So that means there can't be any left for this. Right? In this line, what do I have for a total right now? And so if there's got to be a total of 4, that means there could be 2 imaginary there. And for this line, I have a total of 0. Okay, so here's what we're saying. In this problem, there are 3 possible scenarios on signs for my answers. I could have no positive, 4 negative, and no imaginaries. I could have no positive, 2 negative, and 2 imaginaries, and I could have all 4 imaginaries. Those are my 3 possibilities. Now, that'll be helpful as we go through this, honest. By the way, you see, this is a big one. There are no positive solutions. So when we eventually do Descartes, you know, and get all those possible candidates, I don't even have to try the positive ones, do I? We've already been told by Descartes there won't be any positive solutions. So we just cut those possibilities in half. This is good. Half the work.
How do you do it with measurement?
That goes back to the fundamental theorem of algebra, which says whatever degree the polynomial is, that's how many complex solutions there are. So because this was a fourth degree, the total has to be 4. So I looked and I said, oh, this already had a total of 4, so this is, I can't have any here. So all I did was fill in the imaginary column to get a total of 4. Make sense? Okay. So anyway, do you see how this is, they don't always come out this way, but in this one, do you see how we got no positive solutions? So that means we don't even have to waste our time trying positive solutions. So Descartes has already helped us, saved us half the time. No? I'm gone already? Is that what that meant? Oh, good. I thought it was like, okay, I'm gone. Yes? Uh-huh. Okay. Well, I just got from the original count being 0. Okay. When I did my f of negative x, I remember I came up with a count of 4 sign changes, so I knew I had either 4 or 2 or 0 going down by 2's. You see how I got those? Whatever number you get for sign changes, you have either that number or any number 2 less. So you just keep going down by 2's. So I went 4, 2, 0. Yeah, that's what you missed. Okay. All right, let's go on. Now let's do the rational roots theorem now. Okay, now I got this. I'm going to get rid of this because I need the space. All right, so what are P and Q in this problem? There's P. And the reason I put the 1 in there is because I wanted to identify Mr. Q, right? Okay, so now over here on the left, let's do this PQ thing. Okay, what are all the possible factors of P? Plus or minus 1, plus or minus 3, and plus or minus 9. That's not bad. There aren't very many, are there? Agreed? Do you know of any other whole numbers that divide in even? Okay. And on Q, very simple, plus or minus 1. So what are the possible P over Q fractions? There really aren't that many. You got plus or minus 1 over 1, which is just good old 1. You got plus or minus 3 over 1. And you got plus or minus 9 over 1. So according to the rational roots theorem, there are 6 possible answers. But now this guy down here says, oh no, there isn't. There aren't any positive answers. So you can forget of all these positives up here. So we're down to 3. Now that's really pretty cool. The 3 I want to try are negative 1, negative 3, and negative 9. Right? I'm not going to try positives. Okay. So now let's use what? The remainder theorem. See, we got to put a lot of tools together here. And I realize that sounds very complex. So now, what happens when I plug in negative 1? Let's try negative 1 and see if it works. Well, what do you get? Negative 1 to the 4th is 1. Negative 1 cubed is negative 1 times 6 is minus 6. Negative 1 squared is positive 1 times 10 is 10. Negative 1 times 6 is minus 6. And what do I get? I get a negative 12 and a positive what? 20? So no go. So negative 1 doesn't work. All right. Let's try negative 3. Negative 3, let's just say, what I'm doing is this. I've just been too lazy to write it down. All right. Negative 3, these are going to get bigger. What's 3 to the 4th? Well, 3 squared is 9, and 9 times 9 is 81. Okay, negative 3 cubed is negative 27. And what's negative 27 times 6? I don't know, my head is, we got 42, 4, 162. Okay. Now, negative 3 squared is 9. 9 times 10 is 90. Negative 3 times 6 is negative 18. Okay, what do we got? For positives, we have 170, 180. For negatives, we have 180. Cool. This comes out to 0. We have success. Because f of 3 equals 0, we now know that negative 3 is a solution. And if negative 3 is a solution, what must one of the factors be? X plus 3. Now, I'm running out of space, but let's write that down. All right, now, what's left after I divide in this x plus 3? Well, let's use synthetic to do that. Okay, so I'm going to set up a synthetic problem down here. By the way, do I have any missing values of the exponent? 3, 2, 1, 0. Nope, we're in good shape. So the the coefficients are 1, 6, 10, 6, and 9. And I'm trying the solution of negative 3. Bring down, multiply, add, multiply, add, multiply, add, multiply, and add. Yep, there's my remainder of goose egg, which guarantees that this did work. And now here's what I have left. What is that? That is x cubed plus 3x squared plus x plus 3. Okay. Well, I still have a cubic. Guess what? I'm not done. Now, don't give up on negative 3. It could be that negative 3 is twice. So, this is just some advice from me. You know, the last one we tried was negative 3, and we struck it rich, right? Let's try negative 3 again, only now I have good news for you. We can try it in a lower polynomial, this one. So let's plug in negative 3 and see what happens. Okay, you get negative 27 plus 27. Cool, we're at 0. Minus 3 plus 3. It works again. You see that? So now I know we have another factor of x plus 3. So I'm going to write them. So we now know both of these are legit. What's left now? Now you're going to have to forgive me. I simply don't have enough room to keep all this stuff on the page. I guess I'll just go down lower. So let's do another one. This time, my coefficients are right here. 1, 3, 1, 3. And I'm doing negative 3 again. Bring down, multiply, add, multiply, add, multiply, add. Sure enough, look, 0. That, if I don't get a 0 here, then I know somebody, namely me, messed up. But it worked. So what's left? What is it? Now, can you read this? This is x squared plus no x plus 1. So in other words, it's just x squared plus 1. Who knows how to factor x squared plus 1? Answer is, all of you should. Try. Let's see if anybody comes up with it. First of all, be careful. It's the sum of 2 squares. And we haven't done it for quite a while. It's 2 complex conjugates. X plus I, x minus I. By the way, you could do the quadratic and find out. But I'm going to just write it down. So here, we got it all factored now. Here are the... So we got those two, then we got x plus I, and we have x minus I. We have it completely factored. Now, what are the solutions? Well, this solution is negative 3. This solution is negative 3. This solution is negative I, And this solution is positive I. Okay. Which scenario does that match over here? Two negatives and two imaginaries. Here we go, right here. Problem complete. Now, you see how we had to use a bunch of tools at once there? That's the trouble. These problems take, you know, I mean, here we are. We're almost done with time. And I've only had the joy of presenting a couple of these to you, or one complete one. Well, that's part of the reason I want to spend another day on this. Well, why don't we just stop here and go ahead and open up questions about this. I know I loaded a lot on you today, unloaded, but I don't know any other way to do this. I mean, finally we had to jump into the water, whether or not we were afraid, even though there was a big safety preserver right nearby that we could grab onto. And even though the water looked scary, it's like, hey, you should be able to float through this. In fact, that's kind of cool. It's a big pink bunny I can grab onto. No, I'm just kidding. Yes. The exponents? Yeah, if there's one skip, you really need to insert it. And the reason you need to, yeah, she just asked this question. The exponents have been all nicely lined up in descending order up until now, and we haven't skipped any. What would happen if, like, there was a 7th power and then there was no 6th and went right to a 5th? Well, you know that when you do this, or division, you got to have it in there anyway. So my suggestion would be right away to write a 0x to the 6th and get them all in there. And if they're not in the right order, I would get them in the right order. So I would rewrite it, so I put the highest power first and the next highest power. Before I even do anything, I think I would do that first.
Okay, well, the reason I'm going to like, what you're saying is what they provide, say, like, and provide they're both like negative signs, but then put plus 0 squared, is that screw up the counting, or is that plus an
No, yeah, that's a good, very good point. She's saying if there's one skip, what happens to sign changes? Well, the answer is plus 0 doesn't count for anything. So in other words, if we did insert a plus 0x to the 6th, I mean, I'm sure we put a plus sign there. But when you add 0, have you changed any signs? No. It really isn't that neutral. So when you're counting sign changes, you would just simply not do anything at a 0. That's a very good question. Other questions? My intention is, I'm sorry, we still can go, maybe that's the next thing we should do is work on a couple that you wanted to bring up at the beginning of the period. But I'm going to try to get through 2 more long ones next time. That's about all I probably can do in the time, or maybe 3 if I'm lucky. And then we'll get you guys going on a 3-4 assignment. So, now, you can go ahead and start on one. I mean, it's not like I'm prohibiting you from working on it, but we definitely need more time. Now, there is one more rule I skipped called the bounds. I honestly don't think you need it. And if there is I'll have to look. If there's a section in the assignment specifically about bounds, I'm probably going to ask you not to do that. Okay, questions on the assignment that was due today? Yes? 36? 37. Okay, 3.3, number 37, I'm going to try to do here. Let's see, express, oh yeah, okay, yeah, this language is kind of bad, isn't it? I'll tell you what, I don't have very much time. I got about 12 seconds. So what I'm going to do is show you one like it. Okay, 41, here's what happened when I divided it out. Okay, I got an answer, but it did not come out even, and it had a remainder. Now, how can I write this in that format that they wanted? Except all they're saying is kind of write out the check to your problem. So take the divisor and multiply it by your quotient and just add on the remainder. What? No, in that format, you don't make the remainder into a fraction. So this is just like saying, hey, how do you check a division problem? Okay, you take the answer and you multiply it by what you divided by. Oh yeah, and then add the remainder. Isn't that just how we check a division problem? That's really what the directions. What's in that section by 39, 41, and others? That's what those directions are trying to tell you to do. Sorry, I ran a little over. Thanks for your patience. I started late too. One more day on this. See ya.